Hello and welcome to OpenRelay Screenside Chats episode 7. Today we are taking a step away from OpenRelay specific topics, and we are going to talk about Ethereum events in general. So events are essentially stuff that happens on the blockchain. So you have things like token transfers and 0x orders that get filled and crypto kitties that are born. And then you have off-chain systems that need to know these things have happened. So if you have a token transfer, you may want to process a payment and ship an item because somebody transferred a token to you. So you might have a payment processing system that monitors for token transfer events and then reacts to those things in the real world. For OpenRelay, as a 0x relayer, one of the things that we have to do is when an order gets filled, we need to prune that order out of our order book so that we can not send anybody outdated information. When a CryptoKitty is born, somebody might want to, or the people who manage the CryptoKitties website might want to update their off-chain search engine so that people can see what CryptoKitties exist as soon as they come into existence. One important note about Ethereum events is that they are cheaper than state updates. So absent Ethereum events, you could create a state record on the Ethereum blockchain that said, this thing has happened, and you could go on a recurring basis, check to see if that thing has happened. But Ethereum events are a much cheaper way to accomplish that purpose. So the overview of today's presentation, we are going to look at the event interactions that happen both in Solidity when events are produced and in JavaScript when events are consumed. And then we're going to take a look under the hood at how events are stored on the blockchain and how events are indexed for easy lookup. So we're going to start out with event generation. So this happens in contracts, which are usually written in Solidity. There's a couple of other languages that contracts can be written in, but we're going to be focusing on the Solidity side of things. So here is an example of a Solidity event definition. This is an ERC20 token transfer event. So you can see we start out in Solidity, we declare that we are starting an event. We give the event a name, in this case, transfer. Then we say that this is an address called from, and it is indexed. Then we have our next argument to the event is an address called to, which is also indexed. And then we have an unsigned integer called tokens, which is not indexed. So essentially, when you have a transfer event, you're going to have from, so this is who is sending the ERC20 token, to is who is receiving the ERC20 token, and tokens is the number of tokens being transferred. This will be emitted by the token contract, so the event will also include information about the contract that is emitting the event. I mentioned gas earlier. So emitting any event in terms of gas costs, it costs 375 for any event, plus 8 gas for every byte of data that is not indexed, plus 375 gas for each index in our event, plus 1, because there is another topic that gets stuck in there that is the signature. It represents the signature of the event. So for a token transfer event for an ERC20 token, that costs 1,756 gas to store or to emit the event. By comparison, if you were storing a piece of data, that costs a minimum of 10,000 gas per 32-byte word of data. So to store the same 3 pieces of information, you'd be looking at least 30,000 gas to store that information, where it costs less than 2,000 gas to emit an event about it. So what is the actual emission of the event look like? So in this function, I've made the surrounding stuff small because it's not terribly important, and then I've emboldened the emission of the event. So here we call emit transfer. The account that is sending the the token is message.sender. The account receiving it is this _2 variable, and the amount being sent is value. So that's going to map into the transfer event definition that we had above, and that event is going to be emitted so that it can be received off-chain. As far as off-chain processing goes, any event processing happens off-chain. Events are not accessible within contracts. They are used to capture any changes that happen in off-chain systems, but there is no way to catch an event in Solidity or have a contract automatically react to the emission of an event. All event processing has to happen off-chain. Most event processing tools are written in JavaScript. JavaScript has some of the best tooling for interacting with the blockchain and events in particular. That said, OpenRelay does its event processing in Go. So there are options to process events in languages other than JavaScript, but I would venture a guess that upwards of 90% of the events that get processed for the Ethereum blockchain are being processed in JavaScript. So here is a quick example of what it looks like to process an event in JavaScript. In this case, we are creating a contract object. So if we say web3.eth.contract and pass in the ABI for that contract, and then tell it what address this contract is deployed to on the network we're connected to, that will give us a contract object that we can use to watch for events. So if we want to watch for a token transfer event, specifically where the to index of this event is our current Ethereum account, we set up our contract object .transfer to web3.eth.accounts0, and that will set up an event watcher. We can then say event.watch and give it a callback function. So the first argument to the callback function is an error. The second argument is the log object that was emitted by a contract. So here we're just going to log to, from, and quantity, and we look in the log object. We do log.args.to, log.args.from, log.args.token. And since the ABI up here told Web3 all about this event, this log object has everything already nicely parsed out so that we can just access the to, from, and tokens arguments and just log them quickly. This will continue polling the blockchain on a regular basis for any events that match that description. And it will fire this function anytime such an event happens on the blockchain for as long as this application continues to run. However, if at some point in the future we called event.stopWatching, and we need to give it some kind of callback function because Web3 functions always require a callback, and they will yell at you if you don't provide a callback, even if you don't have anything that you want to do with that callback. Anyway, we call event.stopWatching. That will stop polling the blockchain and stop firing your watch callback function. But that's the basic way that you would process an event in JavaScript. Now, taking a little step further, this is still JavaScript, and we are still processing exactly the same set of events, but this time we're doing it without knowing about the contract and without knowing about the contract ABI. So rather than defining a contract object through Web3, we are setting up a filter to monitor event logs through a lower level function. So here we're passing in the contract address to tell it that we only want events that are emitted by this contract. You do have an option, if you were setting up a web3.eth.filter, not to provide an address contract, like a contract address, as we did here, in which case you would get anything that matched your topics for any contract, regardless of whether or not it's from an address that you're particularly interested in. So then we also specify that a list of topics that we want to match. So here, this first topic that's 0xddf252 blah blah blah, that actually matches the event transfer function. We will look at where this long string of letters and numbers came from in a few minutes, but just know that that means we are looking specifically for ERC20 transfer events. The next line here, we are polling for items where topic 1, actually, I think I wrote this wrong. That should be in topic 2, matches the account 0. Now, so that's our first Ethereum account. Note that topics have to be 32-byte values, so we are prefixing this with a bunch of preceding zeros so that the rest of our event will come at the end of that space. And then null just says that in this next topic line, we will accept anything in that topic position. So that sets up our watcher. And then we call watcher.watch. Again, we have a callback function that takes an error, or receives an error and a log. And then to log the address, we log.topics1. We slice 24, so we're chopping off the first 24 characters of the hex string that would be returned here to get the last 40 characters, which would be the address. We do the same thing for the from value from log.topics2. And then the quantity is log.data, and it's going to be hexadecimal encoded. So we're going to convert that to a big number, doing a base 16 conversion. And that is going to give us exactly the same callback function that's going to log exactly the same information that we logged on our previous slide, but without any foreknowledge of the contract information like we passed in previously. And I'm showing you this slide specifically to kind of break things down a little bit further and explain the underlying parts that got abstracted away for us by Web3. Again, we have watcher.stopwatching if we want to stop polling for these events. Otherwise, Web3 will keep querying the blockchain on a regular interval and giving us these items anytime that they happen. Does anybody have questions on what we've covered so far about how events are emitted in Solidity or how we monitor for those events in JavaScript?
Good so far.
Okay. So now we're going to start looking under the hood. We're going to talk about how events get converted into Ethereum log messages. Events are kind of a Solidity concept, whereas log messages are the underlying thing that gets stored on the blockchain. To do that, we're going to take a look at transaction receipts that contain logs, and they also contain Bloom filters telling us what logs are available in that transaction receipt. Then we're also going to look at the block itself, which has a list of transactions and also has a Bloom filter about all of the logs that are found within that block. And we'll talk about what Bloom filters are for and how helpful they are in a few minutes. So as we break down the event into a log message, the first item is topic 0. So topic 0 was that 0xdd252 something or other that we saw when we were monitoring for an event without specifying the contract information. So that topic 0 is derived by taking the Keccak 256 hash of the string transfer address uint, which is essentially the name of the event, the type of the first argument, the type of the second argument, the type of the third argument, and so forth. Note that the hex representation that goes into topic 0 does not account for the names of any of the values, nor does it account for whether or not those items are indexed. Now, names, I think that makes a lot of sense, that different contracts may give different names to those values. I mean, maybe the authors of those contracts are writing in different languages, and they want those, by which I mean, English versus Spanish versus Chinese, whereas whether or not a field is indexed, I think ought to be included in this, but is not. The reason I think indexes should have been included in this is that a transfer object where there are no indexed fields versus one where there are 2 index fields versus one where there are 3 index fields, those have to be treated in very different ways by the tool that is processing those events. So indexes get slotted into topics in the order that they're listed, where any, and that's this point. So our first object, our first index becomes topic 1, our second index becomes topic 2, our third index, if we had one, which we don't in the transfer event, becomes topic 3, and that's all the topics you can have. You can't have more than the 3 indexes on a Solidity event. And then any unindexed data gets slotted into the data attribute of a log, which is just a long byte string, and each field in a Solidity argument is represented as 32 bytes of the data string. So if we had an event with no indexed fields and these 3 arguments, then we're going to end up with 96 bytes of data and just the topic 0. If all 3 of these fields were indexed, then we would end up with 0 bytes of data and 4 indexes. There's 4 topics. So how we handle those pieces of information depends on whether or not the topics are indexed, or the fields are indexed, which to me tells me that topic 0 ought to change when the indexes change, but it doesn't, so that's something that you have to deal with as you're processing events. You have to sort of validate that all of the topics you're getting, or that you're getting the number of topics that you expect, the amount of data that you expect, and that everything looks like the right information. So you can't take too many assumptions if you are not also filtering on the address that your logs are going to come from. And that's the final point, is that log messages include the Ethereum address of the contract that is emitting the event. So those logs go into what is called a transaction receipt, and every transaction that happens on the blockchain gets a transaction receipt that gets stored in a Merkle tree. So a transaction receipt from an event that I pulled off of the Ethereum mainnet blockchain that has a transfer event looks like this. So a transaction receipt includes the block hash that this transaction was included in. It includes the block number that this block was included in. The cumulative gas used is the amount of gas that had been used in this block when this transaction finished executing. So that's not the gas used by this transaction. It's the gas used by all of the transactions in the block up to this point. From is the account that emitted this transaction. Gas used is the amount of gas used by this specific transaction. And then we get into a list of logs, and it is entirely possible for a single transaction to emit multiple logs. As an example of that, here is a transfer log. So it tells us the address of the contract that emitted this log. In this case, it's a NotCoin event. The topics are the long Kekak 256 string that we looked at, how that was generated a minute ago. And then this is, I think, the from value, the from address and the to address. So then we have the data, which is a hexadecimal representation of the quantity of the token that was transferred. And then we have, again, the log will actually include the same information that the transaction receipt already has, because when you're processing a log, you don't always have easy access to that information. So it gives us the block number, it gives us the block hash, it gives us the transaction hash. The transaction index is, this tells us that this was the 31st transaction processed as a part of block 6,185,919. And then it tells us that this log is index number 17, which means that this is the 17th logged event as a part of that block. Finally, this removed flag would be set to true if this event were being emitted as part of a chain reorganization to tell us that this event was basically unhappening and that there was a chain reorganization that made this event irrelevant. The next thing that we have as part of the transaction receipt is the hexadecimal representation of the Bloom filter. I'm not actually sure what the status is. The 2 is the recipient of, or the contract that is being called to emit this event. Then we have the transaction hash again and the transaction index, which we already saw in the log message. Does anybody have any questions about transaction receipts before I move on? There's a lot of information in here. The main things that I want you guys to understand at this point are the representation of the log within the transaction receipt. No questions? Okay. So then we're going to look at the block header. So every block on the Ethereum blockchain has what we call a block header. I'm going to skip over a lot of these fields because they're not very pertinent to what we're talking about. There's gas limit. That's how much gas this block was allowed to use. Gas used is how much gas this block did use. Then there's the block hash, the log's Bloom filter for the entire block. This is an important point. The miner who mined the block, some information is pertinent to mining and validating hashes, gives us the block number, the parent block. The receipts root is the Merkle tree root for the transaction receipts for this block. SHA-3 uncles is, well, I'm not going to bother with that right now. Uncles are a complicated topic, which are the subject for another video, perhaps. The state root is the current representation of all of the state data stored on the Ethereum blockchain at this point. The timestamp is the Unix timestamp in seconds of the time that this block was recorded. And the timestamp on Ethereum blocks should not be assumed to be terribly accurate. The guarantees that you have are that it only goes up from one block to the next. It can't go down. And generally, the network will reject blocks that they see that have times in the future. So this is going to be sometime between the last block that was mined and now, but that doesn't give you a whole lot of precision. Then there is a list of all of the transactions that are stored on this block. There were a whole bunch, so I truncated this list. But the important one that we're paying attention to is this 0x5c13 blah, blah, blah. That is the event that we looked at, or the transaction that we looked at on the previous slide. And then we have the transaction root and some more stuff about uncles. But that's the important stuff that we're concerned about for the block header. Anybody have any questions about the block header? Again, this is a lot of data here. All right. So a naive approach for doing event processing, and this is not what actually happens, but this is a way that you could find events if it weren't for some of the efficiencies in place. You could iterate over every single block. Then for each block, you could iterate over every single transaction. And then for each transaction, you could iterate over every single log. And for each log, you would match the filters that you provided, and you would return any logs that matched the set of filters that you provided. Obviously, there are a lot of blocks, there are a lot of transactions in each block, and there are potentially a lot of logs in each transaction. So this could be a very time-consuming way to go about finding the events that you're interested in. So this is where Bloom filters come in handy. And for those of you who know me well, Bloom filters are one of my favorite things to talk about. So I am super excited to finally be doing a video on Bloom filters. Bloom filters are a fixed size data structure that's used for probabilistic membership testing that provide constant time lookups. The probabilistic part of the membership testing tells us that there can be some false positives, but the way the system is structured, there can be no false negatives. So false positives would mean it might sometimes tell you that something is a member of a Bloom filter when it has never been added to the Bloom filter. But once something has been added to the Bloom filter, it will never tell you that that thing is not a member of the Bloom filter. So what does that mean? We're going to build a Bloom filter containing a handful of animals, and then we are going to see if certain animals are members of that Bloom filter. So here we have an array of bits, and we are going to take our strings and see and add those strings into our Bloom filter. So for the string dog, we apply 3 hashing functions, and the number of hashing functions, 3 is the number for Ethereum Bloom filters, but the number of hashing functions can vary depending on your Bloom filter implementation. So in this case, we hash the word dog, and that hash is going to map into a particular slot in our bit array. So here we find that it sets this bit for hash 1, and then we apply a different hashing function to the same string and find that it sets a different bit. And then we apply a third hashing function to the same string and find that it sets yet another bit. So the Bloom filter of the list containing only dog is going to be this bit set, that bit set, and that bit set, with the rest of the bits in our bit array all empty. So we have dog in our Bloom filter. Now we want to add a cat to our Bloom filter. We apply the same 3 hashing functions to the string cat, and we see that for the first hashing function, we set that bit. For the second hashing function, we set that bit. For the third hashing function, we set that bit. Now for our Bloom filter that contains both cat and dog, we're going to pull down, okay, this bit up here maps down into that bit down here. This bit down here maps into that bit down there. But, oh, that bit was already set by dog, so we don't need to set that again. And then this, for hash function 3, this bit maps down into that bit. And understand that in my Bloom filter down at the bottom, the colored bits are just there to represent that this has been filled, so that we can keep track just for the purposes of the presentation. I have colored them based on the items that we were adding to the bloom filter when it got added, but it's a bloom filter doesn't know which items set those bits. It just knows that they are set, and there's no coloring of bits within a bloom filter. So now we want to run a test with a bloom filter. So say we want to test and see if squirrel is a member of a bloom filter, our bloom filter. So we do #1 of squirrel, and we get this bit. We check our bloom filter. We see that that bit is not set in our bloom filter. So we know squirrel is not a member of our bloom filter, and we don't even have to check bits 2 and 3 because we've already failed our test. Squirrel is not a member of this bloom filter. However, there is a risk of false positives. Suppose we have a weasel. So we take #1 of weasel, and we see that the first hash of weasel maps down into this bit down here that was set when we set cat. And then we take #2 of weasel, and we map that down here to this bit that was set when we set dog. And then #3 of weasel maps down here to the same thing, to another bit that we mapped when we set dog. And as far as our bloom filter is concerned, a weasel is a member of our set, even though it was never added. That is where the false positives come in. So it is possible with a bloom filter that you could have a report in the affirmative that something is in your bloom filter when that thing was never added to your bloom filter and should not be considered to be present in your bloom filter, but because of the way it is a probabilistic system, there's going to be a certain percentage of things that show up there when they shouldn't. The error rate for a bloom filter is determined by the number of bits in the bloom filter, the number of hash functions that you use in the bloom filter, and the number of elements in your set. So if you know, for example, that you are going to be creating a bloom filter with 2 million items in it, you can pick a number of bits and a number of hash functions that will minimize the error rate for your 2 million item set. And you can basically pick your error rate. So if you want to say, 95% accuracy is okay, then you can have a number of bits and a number of hash functions that is fairly small. If you say, no, I need 99.9999% accuracy, then your number of bits and your number of hash functions is going to have to go way up. Does all that make sense? Does anybody have questions about bloom filters before we move on to how bloom filters are applied within Ethereum?
I'm good.
No, what?
Oh, I was saying I'm good.
Okay. So for what it's worth, bloom filters are an age-old data structure. They have been used in word processors for spell checkers for ages. I'm pretty sure bloom filters are older than I am. They are definitely older than the Ethereum blockchain is, but the Ethereum blockchain makes very diligent use of bloom filters. So I was, as somebody who has been a bloom filter fanatic for years, I was really excited to see that the Ethereum blockchain makes good use of bloom filters. So bloom filters in Ethereum, every bloom filter in the Ethereum system is a 2048-bit bloom filter. And those bloom filters use 3 hashing functions. So every item that gets stored into a bloom filter is going to be hashed 3 times and take up 3 bits. The thing, when you emit an event, the things that get hashed and stuck into the bloom filter are the list of topics and the contract address. So you can check the bloom filter to say, have any events been emitted by this contract, or have any events been emitted that match these topics? Mind you, this is probabilistic. It might, as you were checking the bloom filter, tell you, yes, we have something from that address, when really it doesn't. But the system accounts for that. That just means that we're going to have to do a little bit more work to determine that, no, we don't actually have a log that matches this. So the Bloom filter is a big efficiency benefit. It saves us a bunch of time. But the probabilistic piece, where sometimes we might have false positives, never causes any problems beyond having to do a little bit of extra work. All of the transaction level Bloom filters are added to the block Bloom filter, so we can check to see if any give. So in addition to being able to check, is this filter, are there any logs matching this filter within this transaction, we can also check to see if there are any logs matching this Bloom filter within a given block. So we went over our event processing process absent Bloom filters a little bit ago, and how we had to iterate over every block and every transaction and every log. In this case, we iterate over the blocks, and we check our filter against the block Bloom filter. Only if the block Bloom filter tells us that our filter is matched, then we iterate over all of the transactions in that block and check the transaction level Bloom filter to see if that transaction includes any logs that we're interested in. If the transaction level Bloom filter matches, then we iterate over the logs in that transaction, and we compile a list of the logs that are found in the blocks that matched, in the transactions that matched, where the topics actually matched. And then we return that list of matching logs, which may be 0, even if we had our block Bloom filter or our transaction Bloom filter tell us, give us an affirmative result. It may be that once we actually got in and looked at the logs, there wasn't anything that actually matched our query. And that's okay. That's what Bloom filters are for. They saved us some work from having to look at all the blocks and all the transactions. But sometimes we'll have to do a little bit of extra work looking at specific things to see if they match our requirements. So some other event processing notes. Clients, in the Ethereum RPC system, clients will install filters on the RPC server. The server then tracks events as they come in from the peer-to-peer system against filters, and keeps track of those events with respect to the filter that requested those events. The server discards those events after serving them to a client. So clients will sit there making a recurring request of, are there any new events for this filter? Are there any new events for this filter? Are there any new events for this filter? And if there are, the server will return them and then wipe them out of its own memory. And if there aren't any events matching those filters, then it will just return an empty result saying, nope, no results for that filter. One of the problems with this approach is that filter sessions are stateful. So once you have installed a filter on an RPC server, all subsequent requests must go to the same RPC server. OpenRelay doesn't like that very much. We don't like having individual servers that we're dependent on. So we do not use the install filter paradigm. We just go block by block, and every time a new block happens, we ask our RPC servers, do you have any events that match this filter in this block? It either says yes or no for that particular block, and then we don't ask it again until the next block comes around. So now that we've looked under the hood, we're going to go back through our Solidity and JavaScript definitions and talk about them again and how they pertain to the things that are happening under the hood. So we have an ERC20 token transfer event. So this transfer address uint is going to get mapped into the topic 0 that's going to be stored for the log that comes out of this. The from value is going to go into topic 1. The to value is going to go into topic 2. And the tokens unsigned integer is going to go into the first 32 bytes of data. And since that's all the values we have for this event, that's all the data we're going to have. when it comes down to emitting the event, when the Ethereum virtual machine is processing this code, where we call emit a transfer event, that is going to create a log paired with the transaction receipt for the transaction that is currently being processed, where topic 0 is going to correspond to this function signature. Topic 1 is going to correspond to the address of the sender. Topic 2 is going to correspond to the recipient of this transaction. And the data, the first 32 bytes of the data, is going to correspond to this value. So that is going to be stored in the transaction receipt, basically as soon as this gets executed. And then on the back end, when we have JavaScript that's looking for that information, if we're using a filter here, we ask the Ethereum RPC server, do you have any events where this address, or that were emitted by this address, where these topics are matched, and we want this value and that value. That is going to go in a request back to the RPC server. The RPC server is going to compare those values against block level Bloom filters. If it finds those values in any block level Bloom filters, it's going to go back, iterate over the transaction receipts. For each transaction receipt, it's going to go to the transaction level Bloom filter, do the same checks against the transaction Bloom filter. If it gets an affirmative from a transaction, it's going to iterate over the logs and check the address and the topics against those specific logs. It's going to compile a list, and it's going to return those lists as a result to our JavaScript processor, or as an HTTP response, which is going to invoke this JavaScript callback, which is going to give us our log, and then we have to parse that data back out in order to present it to the user. So then going back up one layer of abstraction, we have our contract information. This is going to make the exact same calls to the RPC server. It's just on the JavaScript side. It says, I know about this ABI. I know what the topic for a transfer, or topic 0 for a transfer event looks like. I know that this 2 maps to a particular topic. So it's going to handle all of those translations so that as we are writing our JavaScript code, we don't have to worry about how that maps to topics and data. We just think about, this is what a transfer event looks like. These are how I want to filter. This is the results I want back. So, broadly speaking, I would recommend people who want to interact with events on the Ethereum blockchain just use this interface. Like, understanding what's going on under the hood is useful for, if you want to implement something like in Go, like I did, to understand what's going on under the hood. It's also helpful, one thing I ran into recently was that because the indexed values don't go into, which values are indexed is not considered in topic 0, an ERC20 transfer event and an ERC721 transfer event look pretty much the same, except that they have a different number of topics and a different amount of data. So if you weren't accounting for that fact, and you weren't providing an address where you were trying to filter for things, you could get some very unexpected behaviors where you were trying to filter for all of the ERC20 transfer events that happen on the blockchain, or all of the ERC20 transfer events that happen where you are the recipient of the tokens. And then you might end up getting some ERC721 token transfer events that don't match your expectations, and your application could have problems and potentially crash. That was a thing that was happening with OpenRelay for a little while, but we fixed it. So anyway, I think understanding what's going on with event processing is very, very useful. Even if you're just writing at this layer of abstraction, it's good to understand what's happening underneath it all. So that is it for my presentation on events. Next week, I think I will probably do an ERC 721 discussion. OpenRelay is just about to launch support for ERC 721 on Kovan. If anybody has any other topics that they would like to see discussed on a Screenside chat, please let me know. I'm available on Gitter or Twitter or email or lots of other places. So, unless anybody has any questions, that's all I've got. All right. Thank you all for coming.